Hello everyone, in this video we're going to pick up where we left off in section 13.3. We're looking at partial derivatives. So example 5, it says find the slopes of the surface f of xy equals to this function at the point 1, 2, 1 in the x and y direction. So we already talked about before, to find the slope in the x direction, we plug in the point 1, 2 into our x partial derivative, and to find the slope in the y direction, we plug in the point 1, 2 into our partial derivative with respect to y. Okay, so let's find our partial derivative with respect to x. So we look at this and we say, okay, 1 is a constant, so its derivative of 0. And then to take the derivative of this with respect to x, I need to do the chain rule. Right, so I get -2 when I bring the power down, and then I leave the x minus 1 alone to the first power, and then the derivative of the inside function is 1, so I just multiply it by 1, so that doesn't affect it, so this is my partial derivative with respect to x. My partial derivative with respect to y, and then I should mention the reason why that's the end of the partial derivative with respect to x is because this term right here has no x's in it, so it's treated like a constant whose derivative is 0. So now I go to find the partial derivative with respect to y. The first term, this derivative is 0. The second term, this derivative is 0 because it has no y's in it. And then now I do the chain rule with this piece right here. So I get -2, leave the y minus 2 alone, and then the derivative of y minus 2 with respect to y is just 1. So now to find the slope in the x direction, I plug in the points. This is my x, this is my y. So I plug in 1 and 2 in. So I get -2, and then I get 1 minus 1, which will give me 0. So that's the slope in my x direction. Now the slope in my y direction, I'm going to plug in 1, 2 into here. So I get -2, and then y 2 minus 2. So I get 0 once again. So my x derivative is 0, which means I have a horizontal tangent. My y derivative is 0, which means I have a horizontal tangent in the y direction. So what does this mean? This means the point 1, 2, 1 is the top of I'll just call it a 3D hill. But if I had some hill, you can think of some peak in the 3 dimension. This would be at the very top, and it would kind of have like this nice like T at the very top of in the x and y plane. It would be a nice flat plane that sits right on top of that hill, and that's what we get from this information about the x and y derivative both being equal to 0. All right, so partial derivatives of functions of 3 or more variables. So the concept of a partial derivative can be extended naturally to functions of 3 or more variables. So in general, if I have w, which is a function maybe even of n variables, then in order to find the nth partial derivative, I just treat the whatever derivative I'm taking the partial derivative with respect to, I treat every other variable like a constant and differentiate with respect to that variable. So for example, here, in example 5, I have a function of 3 variables. So when I go to find the partial derivative with respect to x, I treat y and z with as constants and take the derivative with respect to x. Right? So in order to find the partial derivative of f of x, y, and z, I'm going to, again, pretend that y and z are both constants. So if I pretend that y is a constant and I take the derivative with respect to x, I would just get y here. And then if I were to take the next term with respect to x, there's no x's in it, so it's just a constant, so I would get a 0. And then now the third term with respect to x, that would be z would just be left there, right? So my partial derivative with respect to x is just y plus z. When I find my partial derivative with respect to y, so in the first case I would get x. The second case I would get, now y is the variable, z squared is its constant, so z squared would be my derivative, and then my partial derivative of that last term would be 0 because there's no y in it. So I get x plus z squared. there. And now if I take my partial derivative with respect to z, the first term has no z's in it, so it's 0. The second term is z squared. So again, I take the derivative of that, I get 2z. So I get 2. I leave the y alone because it's a constant, and then z. And then the second term, the third term has just z to the first power, so my derivative is the constant x. All right, so I get 2yz plus x is my partial derivative with respect to z. Okay, so let's look at one that's a little bit more interesting. How about if we find f of z for this function? So in order to find the partial derivative with respect to z, we need to use the product rule, right? Because z is a function of z, and sine of xy squared plus 2z is a function of z, right? So f of z, f sub z of xyz, or the partial derivative with respect to z, is take the derivative of z, which is 1, and then I get sine of xy squared plus 2z, and then plus, I leave the z alone. Now I take the derivative of sine of all of that, so I need to use the chain rule. So I get cosine, and I leave everything inside alone. And now I take the derivative of the inside function with respect to z. In that case, the xy squared is like a constant, and then I'd be left with 2 when I take the derivative of 2c. So if I were going to simplify this, I'd get sine of xy squared plus 2z plus 2z cosine of xy squared plus 2z. So that would be my partial derivative. Okay, so then how about this next example 7 is a function of 4 variables, right? And I want to find the partial derivative with respect to w. So I'm gonna first rewrite. I could try to do maybe like the quotient rule, but notice that this whole numerator has no w's in it, and I want to find the partial derivative with respect to w, so it's kind of like a constant. So I'm just gonna rewrite this as f of x, y, z, w, and I'm going to rewrite it as x plus y plus z, which again is all a constant with respect to w, and then I rewrite this as w to the negative 1, right? Because now when I go to take the derivative with respect to w, I just treat this like a constant, and because this is kind of like if I had something maybe like 2 over x, right? Well, what would you do? You think about it as 2x to the negative 1, and then when you take the derivative, you'd end up getting negative 2x to the negative 2, right? And that's kind of what we'll get here. So in this case, when I go to take the partial derivative with respect to w now, so f of w of x, y, z, w, I get the negative because of the negative 1 that I pull out to the front, right? And then I leave the constant x plus y plus z alone, and then I get w to the negative 2. Right? So what does this end up looking like? This looks like negative times x plus y plus z over top of w squared, right? Which, if you distribute the w, would be negative x minus y minus z over top of w squared if I distribute the negative. So either one of these are equivalent answers as long as you realize you need to distribute that w. Okay, so how about higher order derivatives, right? We know in the case of functions of one variable, I can find the second derivative, the third derivative, all the way up to maybe even the nth derivative, right? We did that with like Taylor series and things like that. So we can also do that with functions of multiple variables. So as is true with ordinary derivatives, it's possible to take second, third, and higher partial derivatives of a function of several variables, provided such a derivative exists. Higher order derivatives are denoted by the order in which the differentiation occurs. So if I have the function z equals f of xy, it has multiple partial second derivatives. right? So if I, because I can take the derivative of with respect to x first, and then I can take it with respect to x again, and that's what I have here in case 1. If I differentiate with respect to x twice, then I find the partial derivative with respect to x, and then I find the partial derivative with respect to x of that, and that would give me the second partial derivative. So I denote that by either by this or by the f sub x, right, or two x's in the subindice there. How about if I took the partial derivative with respect to y, and then I took it with respect to y again, right? So that's differentiate with respect to y twice. So I take the partial derivative with respect to y, and then I do it again. In this case, we denote it by the partial derivative and then y squared, or more common is I put a double y in the subindice. So the other thing I could I could do is like mix them together, right? So first differentiate with respect to x, partial derivative, and then partial derivative with respect to y, right? And in that case, I could rewrite it. I could write it as dy dx, because dx came first, so it's farther to the right. Or I could write it as f sub xy, because I did x first and then I did y. The other thing I could do is differentiate with respect to y and then with respect to x. So I took the partial derivative with y, then I did it with respect to x. In this case, I just flip everything around and get f sub yx. Right? So the third and fourth cases are called mixed partial derivatives. Obviously, you can see why, because I'm mixing x's and y's together. Okay, so to find the second, so the question is to find the second order partial derivatives of f, and then find f sub xy, or the partial derivative, mixed partial derivative f sub xy at -1 and 2. Right? So first, I need to find f sub x, or my partial derivative with respect to x. So if I did that, I would get 3y squared, because that's the constant that goes with x. 2y is treated like a constant, so it goes away. Its derivative is 0. And then I would get plus 10x y squared. Right? And then now maybe I'll scoot this over a little bit, and now I'll do the partial derivative with respect to y. So in this case, I would get 6xy when I took the partial derivative of the first term, minus 2, because there's a y in that second term, and then plus 10x squared y. So I'm going to put like maybe a little vertical bar here, because now I'm going to take partial derivatives with respect to these two. Right? So now let's do f sub x of xy. So what I'm going to do is I'm going to go here to the partial derivative with respect to x, which I highlighted in green. And now I look at this guy and differentiate it with respect to the variable x, right? Treat the y's like constants. So if I did that, then the first term has no x's in it, so it goes away, and the second term looks like 10y squared. So I get that. So that's one of my partial derivatives. And now if I wanted to find my other one, would be I look at the partial derivative x, right? So I'm looking at the green one, and what if I now took the partial derivative with respect to y? So I go to this function that's the green function, which is my partial derivative with respect to x, the first order one, and now I differentiate that with respect to y. So if I did that, I'd end up with 6y, and then plus 20xy. All right. Okay, so then now how about if I look at my y? So I look at my y partial derivative, and now I find, I take the partial derivative with respect to y again. So if I did that, I would get 6x, the derivative of minus 2 is 0, and then plus 10x squared. All right? And now the other thing I could do is go to my partial derivative with respect to y, and this time differentiate with respect to x. So I'll go back to my blue equation there, and I differentiate with respect to x. And if I did that, I would get 6y. The derivative of minus 2 is 0, plus differentiating with respect to x, I would get 20xy. And you should notice something. I'm going to cross out that bar and do maybe a smaller vertical bar. What do you notice? You notice that my f sub xy and my f sub yx are the exact same thing, right? And that will always happen. And that's the next theorem, theorem 13.3. It basically what theorem 14.3 says, and what we showed here, is no matter which order you do it in, if you take the derivative with respect to x, then with respect to y, or with respect to y first, then with respect to x, you'll get the same answer, right? So we see that f sub xy is equal to f sub yx, right? So in other words, the order doesn't matter when we take these, when you start taking these derivatives, right? So that's what theorem 13.3 says. If you have a function of x and y such that the partial derivative with x then y, and then the partial derivative with y then x are continuous on an open disk, right? Because remember, I'm plugging yx or xy values into it, so I look like a plane, right? And so when I'm looking at open disks here, then you can switch the order and they'll still be equal. This also applies to 3 or more variables as long as the second derivatives are continuous. So that's what we're going to look at this next example. We're going to show that all of these are equal to each other. All right, so first let's look at this. Let's show that f sub xz, in other words, when I take the derivative with respect to x and then z, I get the same thing as when I take it with respect to z then x. So let's look at f sub x, right, because I got to do that first. So f sub x, this is my function here, right? Maybe I'll highlight it. That's my function. So if I look at the derivative with respect to x, the y is like a constant, so I get y e to the x, because the derivative of e to the x is x, plus, and now the ln of z is like a constant for x, so I get plus ln of z. And I want to show that f sub xz is the same as f sub zx. So now let's take the derivative of this guy, the partial derivative with respect to x with respect to z. Right? So again, how do I do this one? Now I look at the partial derivative with respect to x and differentiate it with respect to z. So if I did that, the first term goes away because it's a constant, and the derivative of ln of z with respect to z is 1 over z. Okay, so now let's go the other way around. Right? Let's go partial derivative with respect to z first. So if I did that, I'm looking at the blue function now, take the partial derivative with respect to z. Well, the first term has no z's in it, so it's a constant. And then now I would end up with, if I took the derivative with respect to z, the x is like a constant, and then I'd multiply it times the derivative of ln of z with respect to d, which is 1 over z. So I end up with like x over z. So now I want to find f sub zx, right? In other words, I look at the partial derivative with respect to z, which is right here, and now I take the partial derivative with respect to x of that. So look at the orange function here, and I take the derivative with respect to x. Well, that means the 1 over z is like a constant for the x variable, so my partial derivative would be 1 over z. And as you notice here, we ended up finding that f of xz was equal to 1 over z, which was also f sub z x, right? So as we predicted and as we stated before, the order does not matter even in the case of when we have 3 variables. Well, actually, this was the case of 2 variables. So now let's really hop into proving this next piece, which is, or showing this next piece, which is this right here. Okay, so what do I need to do? In order to find f of x, z, z, what do I need to do? I need to go to f of xz, which I'll highlight in orange here, and take the derivative with respect to z. Right? If I did that, the derivative of 1 over z with respect to z is negative z to the negative 2, or negative 1 over z squared. Right? Now let's look at fzxz. So if I wanted to look at fzxz, what I would do is I look at f sub zx, which is this guy right here, which is 1 over z, and now I take the derivative of it with respect to the last variable z, and that would again be negative z to the negative 2, or negative 1 over z squared. So we're looking in good shape. Those two are equal to each other. And now the last one here, I need to find f sub zzx. So with this one, I don't have any help yet, so I'm going to have to keep going. So first I need to find f sub zz, right, because I don't have that one yet. And then I would find this derivative with respect to x, right? So in order to find f sub zz, or the partial derivative with respect to z, I need to look at the partial derivative with respect to z, which is this guy right here, right? And then I need to take the derivative of that with respect to z. So the derivative of the orange function with respect to z, I leave the x alone because it's like a constant, and then I have z in the denominator, so I go z to the, so try that again so we don't have to keep rewriting stuff. I would get negative x, because that's like the constant when I bring the z to the negative 1, right? This is like z to xz to the negative 1. And z to the negative 2. So this looks like x over z to the negative 2, or x over z squared. So now I know what, now I know what f sub z, or the second partial derivative with respect to z, and now I can find the last one here, which was f zzx, right? f zzx. So if I want to find this guy, I go to f sub z, which is this guy right here, and I take its derivative with respect to x. Well, in this case, the x would be like, it would go away, and I just have the constant negative 1 over, oops, should add a negative there, negative 1 over z squared, right? So we showed here, notice that this one, and this one are all the same, right? So we showed that f sub xzz is the same as f sub zxz, which is the same as f sub zzx, right? All of them have 2 z's in it and 1 x, and I can put it in any order, and I will get the same answer. So now this really showed that in the case when I have a third order partial derivative, that no matter which order I take it in, I get the same derivative. All right, that's all I have for this video. Thank you.